In this lecture, I'll explain to you the definition of a category and give you some examples. So a category C consists of, firstly, a collection of objects of C. And secondly, for all objects A and B of C, a collection CAB of what we call arrows from A to B. And the third piece of data that we're given is for objects A, B, C of the category C, and F, a function from CAB cross CBC to CAC. So this function is actually a composition, so we'll call it a composition function. And this function, this composition function is supposed to model the composition of functions. So if f is a function from a set A to the set B and g is a function from a set B to a set C, then g circle f would be a function from A to C. So that's the idea behind this, but here it's just an abstraction. So you have given f here and g here, you map it to what is the image is denoted by g circle f. So a category has three pieces of data: a collection of objects, for each pair of objects, a collection of arrows, and whenever you have three objects, then you have arrows from A to B and arrows from B to C. An arrow from A to B can be composed with an arrow from B to C to give you an arrow from A to C. So this is the three pieces of data. And then there are certain axioms satisfying the axioms. So the first axiom is associativity. For all objects A, B, C, and D, F an arrow from A to B, G an arrow from B to C, and H an arrow from C to D. You can compose these three in two different ways. You can take H composed with G circle F, or you could take H circle G and then circle F. So this should be equal, and this is an equality in CAD. And the second is the identity axiom. It says that for every object A of C, there exists an arrow from A to A such that if I take F circle identity of A, this is equal to F for all F going from A to B for any object B of C, and identity of A circle F is equal to F for all F belonging to C, B to A for any objects B. So this is for any B, for any object B. So this axioms now complete the definition of the category. So category consists of objects and morphisms. Morphisms can be composed and they satisfy the associativity and identity conditions. Let's look at some examples. The most standard canonical example of a category is the category of sets. I'll just denote it by set with an underline. It's the category of sets. What are the objects? All sets. And this underlines why I said a collection of objects. I didn't say a set of objects, because when you start talking about the set of all sets, you run into paradoxes. So the objects are all sets, and given sets A and B, the arrows from A to B is the set of all functions from A to B. And what is a composition? G circle F is the composed function. And we know from set theory that the composition of functions is associative, and of course every set has an identity function. Which takes each element of that set to itself. And this satisfies with this identity function, you can prove the identity axiom for categories. So if you compose with the left or right with the identity function, you get the function that you're composing. That's the most fundamental example. Let's look at more interesting examples that we have already encountered in our study of algebra. So maybe this is examples. You can look at group. Objects are groups. Group GH is equal to group homomorphisms from G to H. Right, you can talk about ring, the category of rings. And ring RS equals ring homomorphisms from R to S. We can talk about, given a ring R, we can talk about the category R mod. Objects are R modules. And morphisms R mod from M to N are R module homomorphisms. From M to N. In all these categories, the arrows are actually functions. The objects are all sets and the arrows are all functions. Let's look at a slightly different kind of example where the objects are not sets. So a category with one object. So recall that a monoid is an algebraic structure. It's a set M together with a binary operation M cross M to M, usually denoted M comma N goes to M dot N or just M times Mn, satisfying just two axioms. First is associativity, which says that Mn k, now you can compute this in two ways, is equal to Mn k for all Mn k in M. And the second is the identity axiom, which says that there exists a distinguished element, maybe I'll call it, let's just call it Em, belonging to M, such that Em dot M is equal to M and M dot Em is equal to M for all M in M. So these two axioms are sort of parallel to the axioms for a category, and not surprisingly, we can construct a category that is associated to this monoid. Given a monoid M, define a category Cm with just one object. Usually we denote it by star, and the arrows from M to M is from star to star is just the set of elements of the monoid M, and the composition map is given by C star star. There's only one object to worry about, so the only composition map that you have to worry about is from C star star cross C star star to C star star, given by n circle M is nm, multiplication in the monoid. And then the associativity axiom for monoids corresponds to the associativity axiom for the category Cm, and the identity axiom for monoids corresponds to the identity axiom for the category Cm. And conversely, given a category with one object, let's call it star, C star star inherits the structure of a monoid by using the composition law. So from the composition law, the category has a composition law, and that gives you a function from C star star cross C star star to C star star, and this is a binary operation which gives C star star the structure of a monoid. It's a monoid because the associativity law for the category gives you the associativity law for the monoid, and the identity axiom for the category gives you the identity axiom for the monoid. So what we see is that categories with one object are the same as monoids. Now let's look at a somewhat synthetic appearing example. So consider the directed graph this sort of a visualization of a category. So this graph has three vertices, 1, 2 and 3, and we have an arrow from 1 to 2, an arrow from 2 to 3, and an arrow from 1 to 3. And we have an arrow from 1 to 1, we have an arrow from 2 to 2, and an arrow from 3 to 3. So here I will call this arrow A, I'll call this arrow B, I'll call this arrow C, I'll call this arrow identity 1, I'll call this identity 2, and I'll call this identity 3. You can probably guess the category that I'm going to construct. Consider the category whose objects are the 3 points 1, 2, and 3. So in this case, the objects are again not sets; they are just abstractions. I mean, they're just symbols. And given two objects, C x comma y is the set of arrows from x to y. And so for example, C1 comma 2 is just singleton A, whereas C2 comma 1, well, there are no arrows from 2 to 1, so this is the empty set. So it's quite possible in a category for the collection of arrows between two objects to be empty. And composition is sort of uniquely defined. Because between any two objects there's only one arrow. So if you want to compose B circle A, then it must be C, because there's only one arrow from 1 to 3. There's only one possibility for composition. Now you need to check that composition is always defined. That is, given any two arrows in this category, you can compose them. So for example, compatibly. So if I have an arrow from 1 to 1 and arrow from 1 to 2, I can compose them. A circle identity 1 is A. And so this in fact is the identity arrow of the object 1, and so on. So I leave the details to you. Check that C is a category. This is a special case of a more general category that is associated to a partially ordered set. When we studied Zorn's lemma, we saw the definition of a partially ordered set. We'll use that to construct a category here. Let P be a partially ordered set. Define a category which we'll denote by script P, whose objects are the elements of P. And given PQ in P, I want to say in the poset P, the arrows from P to Q, there's going to be only one arrow which I will denote by, say, APQ if P is less than or equal to Q, and no arrows if otherwise. And the composition is given by so now the only way that you can have an arrow from P to Q and an arrow from Q to R is that P is less than or equal to Q and Q is less than or equal to R. Then the composition of A QR with A PQ is the only possibility, which is A PR. There's only one such possibility. And of course, note that in a poset, P is less than or equal to P for every P in a poset P. So there is APP in PPP, and APP is the identity of. With this, you can easily check the axioms for a category are satisfied. Now, this category that I defined on the previous example is a special case of this category associated to the poset. The example on the previous page comes from the set which has 3 elements, and 1 is less than or equal to 2 is less than or equal to 3. It's a total order on 1, 2, 3, and of course 1 is also less than or equal to 3. So that relation gives rise. Of course 1 is less than or equal to 1, 2 is less than or equal to 2, and 3 is less than or equal to 3. So maybe the best way to write this is that 1 is strictly less than 2 is strictly less than 3. That's a linear order. And if you look at it, this is what we would call A12, this is what we'd call A23, this is A13, and this is A23, this is A22, this is A11, and this is A33. The next few examples are really ways of constructing new categories from old ones. So the first is the opposite or dual category. So given a category C, C-op is the category whose objects are the objects of C. And given objects A and B, which are also objects of C-op, the arrows from A to B in C-op are declared to be the arrows from B to A in C. And the associativity law for C turns into the associativity law for C-op. And the identity axiom also turns into the identity axiom for C-op. So I'll leave it as an exercise for you to check that C-op is also a category. Okay, the next construction of a new category from the old is the product of categories. So given two categories, C1 cross C2 is the category whose objects are pairs A1, A2, where A1 is an object of C1 and A2 is an object of C2. And given so we should also say what morphisms are. And so C1 cross C2, the morphisms from This is A1, this is A2. So we have an object A1 comma A2 and another object B1 comma B2. Then a morphism from A1 comma A2 to B1 comma B2 is a pair, consists of pairs F1 comma F2, where F1 is an arrow from A1 to B1 and F2 is an arrow from A2 to B2. And the composition law is given by G1 circle G2, G1 comma G2 circle F1 comma F2 is G1 circle F1 comma G2 circle F2 for F1 F2 in C A1 A2 to B1 B2 and G1 G2 in C B1 B2 to C1 C2 for any objects A1 A2 of A1 B1 and C1 of the category C1 and A2 B2 C2 objects of the category C2. And again, it's fairly straightforward to check that with this specification we actually get a category. So the associativity and identity axioms are inherited from the categories C1 and C2. Now we come to the definition of subcategories, which is the last construction of a new category from an old one. Given two categories, C1 and C2, we say that C1 is a subcategory of C2. And we just use the subset notation for this. If, the objects of C1 are a sub-collection of the objects of C2. Then for all objects A and B of C1, the arrows in C1 from A to B is a sub-collection of the arrows in C2 of A to B. And the third property is that given objects A, B, C of C1 and morphisms F, C1, AB, G, C2, AB, C2, C1, BC, we have G circle F. This is the composition in C1AC must coincide with G circle F in C2AC. In other words, the composition maps are compatible. This is an example of a subcategory. So let's look at some concrete examples of subcategories. So the first one is, so let C1 be the category of all sets. And I'll define a subcategory of it. Fi it's Fi is short for finite injective, be the category whose objects are finite sets. And arrows Fi AB is all injective functions from A to B. And let's define another category, FB be the category whose objects are again finite sets and FB AB are bijective functions. A to B. You need to check that Fi and Fb are indeed categories, but that's not difficult. You just need to note that a composition of injective functions is injective, and of course the identity function is injective, and here the composition of bijective functions is bijective and the identity function is bijective. Then we have a hierarchy of categories here. Fb is a subcategory of Fi, and Fi is a subcategory of the category of sets. And there's a slight difference between these containments. Here even the objects are not the same, but we are restricting ourselves to finite subsets. So the collection of objects here is smaller than the collection of objects here, but in this containment the collection of objects here is the same as the collection of objects here. What we have changed are the arrows. So in the definition of a category, it's not just important what the objects are, it is equally important what the arrows are. And now let me give you one last thing which I can put in between here, and I will define a category of finite sets. So F set is the category of finite sets. Objects are finite sets, and if you have two finite sets, the arrows from A to B are the same as the arrows from A to B in the category of sets. So all functions from A to B. When you have this condition, this is the notion of a full subcategory. So you've only restricted the objects, but you have whenever you have two objects in your subcategory, the arrows are the same as in the larger category. So what we have is that F set sits in between Fi and set. Oops, let's just and so we can formalize this notion of full subcategory into a definition. C2, a subcategory of C1, is said to be a full subcategory if C2AB is C1AB for all objects A and B of C2. So the objects get restricted, but the arrows do not.